How does plasticity explain why materials break differently? Imagine bending a paperclip back and forth until it snaps, or stretching a piece of rubber until it permanently deforms. These everyday examples show how different materials respond to stress. Today, we're exploring how the property called plasticity helps us understand why some materials break in gentle, ductile ways, while others shatter suddenly and catastrophically. Plasticity is a material's ability to undergo permanent deformation without breaking immediately when subjected to stress beyond its elastic limit. When you apply force, most materials first stretch elastically, meaning they bounce back to their original shape once the force is removed. But if the force exceeds a certain point, called the yield point, the material starts to deform plastically. This means it changes shape permanently. Materials with high plasticity, like many metals and some plastics, can absorb a lot of energy by stretching or bending before they finally break. This process is called ductile failure. You see this in metals like copper or aluminum, which bend and stretch, giving warning signs before they snap. These materials tend to crack slowly, allowing time for detection and prevention. On the other hand, materials with low plasticity, such as glass or ceramics, don't stretch much at all. They tend to break suddenly and without warning, a failure called brittle fracture. When these materials are stressed, they don't deform much before breaking, often shattering into sharp pieces. The microscopic reason behind plasticity involves the movement of tiny defects in the material called dislocations in crystalline metals. These dislocations slide along specific planes, allowing the metal to stretch without cracking. In polymers, plasticity comes from long molecular chains sliding past each other, which can also lead to slow deformation over time, known as creep. Temperature plays a big role in plasticity too. Metals become more ductile at higher temperatures because the atoms can move more easily. Conversely, at lower temperatures, they become more brittle and prone to sudden failure. Flaws like microcracks or environmental factors like chemical exposure can also influence how plastic deformation develops into a fracture. Understanding plasticity helps engineers choose the right materials for different jobs. For example, they might select a ductile metal for a bridge to absorb stress without breaking, or use a brittle ceramic for a cutting tool that needs to resist sudden fractures. For plastics, knowing how they deform and crack under stress helps prevent slow failures like cracking or creep over time. In essence, plasticity controls whether a material will bend and stretch or snap suddenly. It explains why some materials give warning before breaking and others do not. Recognizing these differences helps us design safer, longer-lasting products and better predict how materials will behave under various conditions.